Hello everyone, I'm Bowei, a third-year PhD student from Cambridge. In this talk, I will present my recent work on the Axion Monodromy inflation with Zhang and Enrico. Although this may seem like a specialized study, we hope to use it as an opportunity to discuss some more fundamental issues in inflation model building. One of the goals of studying cosmology is to prove Planck-scale physics through cosmic inflation. A common paradigm is a top-down approach, where inflation models are constructed from a UV theory, and their observational predictions, such as the correlation functions, are then compared with data. However, when constructing these models, researchers often make significant assumptions that may overlook very important UV-related physics. This may lead to missing observational signals linked to high-energy physics. We highlight these issues by using Axion Monodromy as an example. Firstly, I will give a brief introduction about the previous work on the Axion Monodromy inflation, which is inspired by string theory and has been regarded as one of the most successful physical realizations of inflation from UV theory. The starting point is a 10-dimensional supergravity, where we have a 4-dimensional physical spacetime and a 6-dimensional Calabi-Yau manifold. The compactification of the extra dimensions give rise to a large number of fields, including axions and moduli fields. Axions corresponding to integrating gauge potential over non-trivial circles in X6, and moduli fields control the volume of these extra dimensions. The resulted 4-dimensional effective theory, including a canonically normalized axion, and the lightest modular field takes this form, where we introduce the scale lambda to control the coupling strength. The axion potential is characterized by a cosine oscillatory correction on top of the slow roll potential, which means the continuous symmetry of axion is broken into the discrete one by non-perturbative effects. A two-field inflation model is not too bad, but people wanted it to be even simpler. By demanding the mass of the modular field to be large, a common law is that the modular field can be seen as decoupled and can be integrated out. Then we get a single-field inflation model. Based on, this one is maybe familiar to many people, based on this model, predictions of the primordial power spectrum and bispectrum have been made. For example, in these papers, both are characterized by a cosine log oscillations of the co-moving wave number k. For Euro multifield models, the stabilized heavy fields do not affect the low energy single clock theory, so integrating them out is safe. However, for Axion monodromy, situations become more subtle because the background oscillations introduce a new scale, the frequency, which can be comparable with the mass of these massive fields. This new scale may play an important role in the system and lead to the possibility to break down the single field description. Can we still integrate out the heavy fields? If we can't, are there any UV-sensitive signatures in cosmological observables? To answer this question, we systematically investigated simple but general two-field extensions of Axion monodromy with the perturbation theory. The model we study is the same one that appears before, with one axions and the lightest modular fields coupling with each other at kinetic term. These fields are decomposed to classical background and quantum fluctuation. For the classical background, we consider the zeros and the first order. A naive expectation is that the motion is only along phi direction. Before we go any further, we summarize the conventional definitions and assumptions below. In the first one, we define the dimensionless frequency of oscillation, which is supposed to be large. The second one guarantees the monotonicity of the potentials. The third one and the fourth one are required for the controlled computation and the stability of modular fields. The last one describes the hierarchy of energy scales. Now let's start to solve the background dynamics. There are three equations of motions. which are Euler-Lagrange equation for both fields and the Friedmann equation of the total energy. Substituting the background fields into these equations, solve them order by order, we find the zeroth order solutions for phi describe the standard slow roll motion, and that for rho represents the centrifugal force, which stabilizes the modulus fields. As a first order, we find oscillations of the axion velocity as expected. However, we also find oscillations on the modulus directions with the same frequency. The trajectory with wiggles is plotted here. An intuitive explanation is when the axion velocity starts to oscillate, the centrifugal force due to the kinetic mixing drives a deviation from the stabilized position of the heavy field. Then the modulus starts to oscillate, and this non-trivial trajectory will finally lead to enhanced mixings of the quantum fluctuation. Our next purpose is to determine the mixing terms of quantum fluctuations. In flat gauge, the interactions between the quantum fluctuations of axion and modulus can be easily seen from the action. However, this does not determine the mixing of inflationary observables, the primordial curvature perturbations zeta, because in this multi-field context, the primordial curvature perturbation is not directly related to the fluctuations of the axion. To resolve these subtleties and determine the interaction in terms of zeta, we started with the covariant formalism of multi-field inflation. In this method, points on the trajectory are defined as vectors on a two-dimensional hyperbolic field space. At each point, we define the tangent unit vectors along the trajectory and the normal unit vectors, which is proportional to the trajectory. The curvature perturbation is then related to the quantum fluctuation component on the tangent directions. Here we define the turning rate as a product of the tangent vector and the covariant derivative of the normal vector. This quantity describes the deviations from the geodesic motion and is closely relevant to the coupling stress. In this case, the turning rate can be divided into a constant part and a time-dependent part, which oscillates over cosmic time. Then we adopt the EFT of inflation approach introduced by this paper. By taking the unitary gauge, the field fluctuations along the trajectory vanish, so we can write the field vector this way, and all fluctuations are then captured by the isocurvature modes, sigma. The interaction operator linear in sigma can be determined to be this EFT operator. The coupling lambda is proportional to the turning rate, so it is also highly oscillatory. To relate this with the primordial curvature perturbation, we perform a gauge transformation to bring back the Goldstone boson pi of the time diffeomorphism. Substituting this back into the EFT operator, we found we could directly write down the linear mixing term and the cubic interaction term. However, are these the most important interaction terms? The answer is no, because when we move to the Goldstone gauge, the time-dependent coupling lambda is also got a shift of pi and leads to another cubic operator. Considering the time derivatives acting on a highly oscillatory function leads to an enhancement by the frequency, this cubic operator is even more dominant compared to this. The same type of operator was also noticed by Lucas in a pure EFT framework. Now we have solved the model and determined the mixing terms explicitly. We can now address the first question: can we still integrate out the heavy field? To begin, we write down the equation of motion for the isocurvature field sigma, incorporating with the linear mixing term. In non-oscillatory cases, a common assumption is that sigma double dot is much smaller than the mass square sigma. Under these assumptions, we can approximate the solution of the isocurvature modes to be this. Substituting these solutions into the perturbative action, we find the reduction of the Goldstone sunspeed is negligible. At first glance, this suggests that the single field description remains valid. However, in axion monodromy, particularly when the oscillation frequency becomes comparable with the modulus field, these assumptions break down. The previous argument for integrating out the heavy field no longer holds. Instead, moduli fields are continuously excited by the background oscillation, meaning that the single field EFT is no longer valid, and the mixing terms become significant. In the last part, I will summarize the observational signatures associated with the oscillatory background and heavy moduli fields. At EFT level, our computation leads to a cosmological collider model, where the primordial curvature perturbation mixes with a massive isocurvature fields, and their couplings oscillates over cosmic time. The power spectrum and bispectrum of this system has been analyzed by Zhang and his collaborators using the yin formalism, focusing on the resonance effect between massless fields, massive fields, and the oscillatory background. With the recently developed bootstrap approach, we can now derive the full correlators. The squeezed limit result is presented here with this plot. In this template, we can observe the standard cosmological collider signal, a scale invariant oscillation of the form cosine log k3 over k1 but with a shifted frequency, and additional scale dependent corrections induced by the oscillatory features or oscillatory backgrounds. In this plot, the cosmological collider signal appears along these directions. These directions, and the resonance features is captured along this direction. By setting the frequency in alpha equals 0, we recover the standard cosmological collider signal, which is exponentially suppressed by the mass of the heavy field. However, when the oscillation frequency becomes comparable with the mass, the suppression is softened by the resonance effect, potentially leading to an observable cosmological collider signals. This result also aligns with the finding of Zhang et al. In their 2022 paper. To conclude, let me summarize the key takeaways from this work. By explicitly solving a two-field inflation model, we have shown that the periodic modulations of axion potential continuously excites the heavy moduli field, breaking down the effective single-field description. From this example, we learn an important general lesson. In any multi-field inflation model with massive fields, if the background introduces an energy scale comparable with the mass of heavy fields, one must be extremely cautious when integrating all those degrees of freedom. Neglecting their effects could result in an incomplete or incorrect effective field theory. Using a bootstrap approach, we find that the model can generate an unsuppressed cosmological collider signal, even for a very large mass. Provides exciting possibilities for detecting primordial non-Gaussianities or cosmological collider signals in upcoming CMB theory. Let's finger cross. Thank you for your attention. I would be happy to take any questions during the discussion session.